Okay, good. So welcome to lecture number 11 of NLP with deep learning. And as I said last time, we're going to shift from, let's say, core techniques in NLP and deep learning to something which is more, let's say, praxis-oriented, like something which is actually used in the also in the, quite a lot in the industry and in real cases. But there's also some research behind, and as you will see, things that we take for granted these days are not at all actually. So these concepts are, just a few years around here, and we're just using them extensively. So we're going to be talking about retrieval augmented generation. Okay, just a quick raise of hands who has heard about RAG. R-A-G. Okay, cool. That's good. So let's get jump on that. So we are talking about big, large language models, and they're just huge, so many parameters and things like that. And we can fine tune them on task. We can do translation, generation, all these sorts of things with fine tuning, in context learning, instruction tuning, and all these things. So, and one of the important functions we're using them is to actually fill some. Like we have some information needs. Like typically, it's question answering. You want to ask questions, like, and how do you ask questions? You could Google for, like for many questions, or you just use AI. I mean, what's better? It depends on the use case and on the quality of whatever search engine and stuff like that. But the thing is, like, sometimes you can actually open up Wikipedia. I'm actually like wondering who is asking where is the Louvre, sorry my French, Louvre, how is it pronounced correctly? Louvre, thank you. Museum located. This is a stupid question. Like, I'm assuming like everybody should know this, but let's say it's some other name, museum, whatever, and you're interested in that. I wouldn't maybe go for just Wikipedia and just type it in, but I don't know. Like people have different information needs, so I'm not judging anybody. And let's consider this as a fair question to ask, right? And we can actually ask a LLM to answer these questions, and we can just prompt LLM. We can just prompt LLM with this question, and the LLM hopefully maybe will able to answer this question. So this is like very simple prompting. We can actually prompt LLM to answer factoid questions, and under the assumption that the LLM has been so-called instruction tuned. So as we were discussing last time, if you take just a vanilla LLM, like pre-trained as a language model, predict the next token, most likely it won't be able to generate meaningful answers to this. It will just continue, spitting out the text, which is most likely to appear after this question. It could be the answer, but most likely not. So what we need to do is to do instruction tuning. We are talking about this reinforcement feedback from human learning and things like that, where you say like, oh, there are some instructions, and be a nice LLM in answering these sort of information needs and instructions given. But provided you instruction tune in a model, it could actually answer the question. And how does it do? Basically this would be a prompt. So there's the LLM, and we say, okay, this is the first tokens in the prompt, and then generate the next tokens, and then there should be the answer. And surprisingly, like, why do you think this actually can work? Why do you think that LLM actually can answer factoid questions like that? What's the reason? This is just a language model. How is it possible that the language model can actually answer such questions? Yeah. The answer is in the training data. And the LLM has seen a lot of facts in the pre-training data, most likely including the location of the museum, and it has been encoded in the parameters. So somehow this is very interesting. So not only the language model is learning things about language, words, syntax, semantics. We had this example of BERT kind of discovering syntactic relations between words in the attention heads. So not only that, but it also learns facts and stores facts, which could be a good thing or a bad thing depending on your, how you look at this. So it has stored it in the parameters, and in fact, so there's a lot of research, contemporary research, in looking where these factual knowledge facts are stored, and one of the examples is is the group from Jotam Delinkov in the last few years looking into how to manipulate factoid knowledge in language models. And they found out in one of these early papers that they are stored in the feed-forward layers of the transformer. So if you recall the transformer layers, in each transformer you have the antenna heads, and then you have the feed-forward. And the factoid knowledge so I mean, this is not like a hard fact. I mean, how a language model stores a knowledge over 300 billion parameters, it's kind of tricky question to address, but you can do research about this, and they found out it's in the feed-forward layers. And it's actually not easy, but it's possible to manipulate this knowledge. So there is a whole field of manipulating factoid knowledge in language models, where you can basically take the parameters of the network, go somewhere, like go to the feed-forward network, for example, change something in there, and the model will no more remember where the louver is located, or it will change it to some other information. So it's pretty cool. You can do this, manipulating. So far so good. It remembers things. It remembers also like your personal data. So if you feed the pre-training data with something confidential, you are running in problems, maybe. So, and that's, if you're interested more in that, like privacy issues of LLMs, I'm teaching next semester privacy preserving NLP, so happy to see you there. So we'll be speaking like the whole semester about privacy and how to prevent it and how to protect it. But anyways, the problem is, I mean, we have trained now, let's say we have trained a huge model, GPT-4, half a year, training lots of millions of dollars. And then you want to answer it factoid questions, and then the problem is, there's many problems actually. There's many problems with answering this question. So we're gonna tackle 3 of them, but maybe like quick raise of hands. So what's the problem of answering factoid questions that you absolutely encountered in your real life using these? Yeah. Hallucination. So what is hallucination?
For the location of the Ruhr museum, and it says it's based in Berlin, for example.
That's right. So they make up facts, of course. Why is it so? It's also like, it's an interesting research question. Why LLM hallucinate? Like, is there a reason? And there's multiple hypotheses, multiple kind of research directions into that, but the fact is, sure, I mean, they are instructed, a model is instructed to be helpful, so it's penalized by the definition if it's not helpful. I mean, you're optimizing the loss, and if the loss is high for your training data, it's giving the signal back like, oh, the answer wasn't helpful for the model, and the model should learn this. So you're penalizing for not answering correctly, which means like the model will try. I'm not personifying the models, but it will try to please you in a way, like, oh yeah, and here's the answer, and everybody knows that these days. So it's not faithful to the facts of the world, like Ruhr is in Berlin, yeah, or Greenland belongs to USA. Oh, that's an interesting point, right? So we'll get to that in the next slide. So, and the reason is also like one of the latest research works is just this paper, if you're interested. It's that the feed-forward layers, which kind of store this factual knowledge, they fail to recall this knowledge. So somehow, the model is not capable, even though the information is stored, the model is not capable to pull it up from the parameters somehow. As I said, it's like active area of research. Well, problem number 2, not Greenland, not yet, but problem number 2, and I mentioned this already with these sensitive data. So the problem number 2 is that just a generic language model, it cannot answer anything about your proprietary data. So for example, I don't know, what could be proprietary data? You want to search your emails, let's say, like answer questions about your emails. You have like 300,000 emails, and you want to, I don't know, ask like, oh, when did I email Joe? Whatever. Or, I don't know, some healthcare data and stuff like that. So there's a couple of examples you can come up, like personal emails. Companies might have internal documents with answers to customer service and so on. And legal firms, legal companies they have their own kind of collection of data. And the assumption is, or the hope is, hopefully, none of this data was in the large web-based corpora for language model training. I mean, that's the assumption. Like, if you're a company, of course, you don't want to just put your stuff on the internet for OpenAI or Google just to train a Gemini on that. You want to keep it for yourself. So the problem is, you have a database you want to kind of use for, answering questions or whatever, but you cannot use just a out-of-box web pre-trained language model. Okay. So problem number 3. So fair enough. I mean, proprietary data, it's a thing. I hope you agree with the last point. If you don't agree with the last point, don't come to the lecture next semester, because privacy matters, like proprietary data matters, and we should kind of we should be serious about it. Not everything should be in public on the internet. The problem number 3, I mentioned Greenland. So what's the problem with that? Like, what's the problem? Why if you ask LLM, like, is Greenland part of the US? Yeah.
Maybe you ask question 2 months later, and Greenland is now part of the USA. One is not capable of presenting that information for us to trading that clear data.
Exactly. So what's the cause of that? The cause is basically, you're right. I mean, the cause is facts are changing. Like, who is the president of the US? It's changing every 4 years, or of the US. Like, the US is a bad example. I mean, we're in Europe. So who's the premier minister? The minister, how's it called? Anyways, like Michael Madsen. How's it called in English? Premier minister, the minister of, the head of the government. Let's put it like that. So it's changing every 4 years, so stuff like that. In the US, it's a different story. In North Korea, it's a completely different story. But these facts are changing, or whether some, country belongs to a particular state or not. And of course, you train your model once, and that's it. I mean, you have one shot, so to say. You consume the whole internet, and then everything will change. So it's basically a static knowledge. So it was pre-trained once at a particular time, and that's it. And it's fixed, and it's kind of baked into the parameters. And of course, you can like train the model every month from scratch, but it's very costly. There's attempts to do something which I mentioned, like the touching the knowledge and changing into the parameters. It's possible. There's also the whole field of research called machine unlearning, where you try to unlearn facts and learn again. I mean, I'm serious. It's a really it's an interesting topic. Like for GDPR, if you want to have your data be forgotten by a company, and the company spent like $500 million on training the model, I mean, the chances are they won't train again. So there has to be another efficient way, like unlearning. Anyways, so static knowledge. So these are like the main, I would say, 3 problems of using static LLM for answering factoid questions. So any other that you might encounter? I mean, I would say like they would fall into these categories. So one solution to these problems, as I said, there's multiple solutions, but one of these solutions, which is kind of very efficient, is retrieval augmented generation. So the idea here is actually very simple at the end. So we give the language model not only like itself, like the parameters and all the information in parameters, but also some external sources of knowledge, such as a collection of documents, and we use these documents in answering the questions. Like basically, there's 2 steps only. We use some techniques from information retrieval, which we'll be talking later in the first part of the lecture, to find the documents that are likely to have some information that might help answer the question. So for example, if you're going to ask a model which was trained half a year ago, in 2 months from now, whether Greenland is part of the US or Denmark, then you might want to put it, just have a collection of news articles, for example, and fetch some news articles that are related to this question, and the model should be able, based on this new information, kind of make your answer more faithful or more truthful. And there's numerous other use cases. And once we fetch these documents, the LLM should be able to generate the answer given these documents. So that's kind of very simple idea right now, and it's actually working quite well. So let's talk first about the the information retrieval part. So I'm just wondering, have you had something along like information retrieval in other courses? That's good. I think it's good to talk about information retrieval. I mean, in databases? It's sort of like getting information, but I don't know if in databases you talk about like document retrieval and stuff. Yeah, sure. Okay. So let's see. I mean, maybe there will be an overlap, maybe not. So information retrieval is basically, it's an old concept which we've been using for, I don't know, 60 years now. No, 20, 50 something years. So it's very simple, like image in web search. So this is the like the premium example of information retrieval. So the typical web search, not AI powered, just plain old, I don't know, Google 5 years ago, for example. Okay, so, or do you use, okay, I'm just wondering, like, do you use something else than Google? So everybody's Googling for searching. No, what do you use? Say again? I don't, sorry. Firefox. No, I mean like a web, like the search engine. Google. Yeah, okay, good. Oh, I'm happy to hear that. So, I mean, I'm not the only person not using Google. Okay.
There's also start page, which doesn't, everywhere where you search something on start page, you will get the same result. It doesn't take preferences or something.
Yeah, exactly. So there's alternative search engines which are worse. No, I mean, not really. Actually, to be honest, I stopped using. So side note, off record, I stopped using like Google, like Googling for everything like 10 years ago, and say like, oh, DuckDuckGo, privacy, and blah blah blah, and it was horrible. Once you get used to it, it's actually very powerful. And whenever I try now search in Google, it's like, Jesus, it's really horrible. Like the results are actually much worse than I'm used to. Well, anyways, it's preferences, but web search is a thing. You have a keyword queries, and you want to find documents which are relevant. So typical web search, and I want to find relevant documents. So the idea is as follows. So we have this query. I don't know, a couple of keywords, museum, Louvre. That's enough. Okay, I mean, you should be able to find the pages about like the museum and where it is, or location, museum, Louvre, whatever. And of course, we want to process the query in some way. And usually we get, because we like to work with vectors and some mathematical representation of stuff, so we get a query vector. And then we have the document collection, which is the internet. Let's say if you're a search engine, you have the internet. You want to process your documents somehow into something called document index, so it allows you to be efficient in finding the documents. But basically, this is you want to represent the documents also as a vectors, or basically some vectors or some meaningful representation in numbers, which allows you to like do the search, basically do the matching or finding documents which have good relevance score according to your query. So I hope this is not surprising in any way. It's like common sense. You have documents, you want to find the most relevant, and what you want to do at the end, you want to rank them. So everybody knows this, of course. In DuckDuckGo, the first hit is the best kind of. It's not ad, at least, or is it? Is there advertisement? There's advertisement in Google. Like the first 10 hits is advertisement. Then you have something, I don't know. I don't care. So, but you can rank these documents, and the idea is, I mean, of course, not everything is web search. You might have actually. Have you tried to search something in the library here, like the web interface of the library? Yeah, don't do this, okay? Or have you tried to search something on the university website? Yeah, yes, no, that's really horrible. This is a true experience of pure information retrieval based on keywords, which is so bad. Because you search for, I don't know, I was searching for something like super common, and I got a PDF document from some very weird Fachbereich from 2014 or something like that as the first hit. And it's like, geez, no. Anyways, so the idea is you get ranked documents, and what's on the top should be like the most relevant to your query. Okay, so the idea is now, how do we do these things? How do we get a query vectors? How do we get the vectors of the documents? And how do we get the relevant scores to get ranked? I mean, these are the technical questions we need to answer. And of course, this will be relevant, well, not only to web search, but also for rec, of course, because we want to search some documents that are relevant to our query first, and then we can generate the answer based on these documents. Why is it so? Why cannot we just say, oh, LLM, here's the internet, and here's my query, generate the answer? Why not? Why do we have to search for some relevant documents first? Yeah?
The context will be blown up if we just put in the whole internet and have not searched for the most relevant documents before.
Yeah, so what is the context window of like big LLMs?
I mean, it's from 250,000
Roughly.
up to 1 million.
I think like, okay, 1 million is really large context. So what do we mean by context? It means like how many tokens you can fit in the prompt. This is the context size, basically. Could be like 30,000, 60,000. 1 million is like really extreme, but I trust you. So maybe there's like...
Google Gemini 2.5 has 1 million context.
Really? Wow.
Yeah.
Okay.
Also Sonnet 4.5 from Retrieval also.
Okay, so you can go really crazy, but imagine you have 1 million tokens. I can guarantee you won't fit the internet in 1 million tokens ever. You won't fit the internet in the context ever, and it would be actually unwise. It would be like really wasting the resources, because there's just this is much easier to find the relevant document. So this is the idea why we need to find these documents first. So how do we find relevant documents? So the goal is assign a score to each document for whether it meets the user information needs, and yeah, I mean, how do we develop a score to measure user information need? It's kind of very complicated, and it's what is user information need? And there's lots of, I mean, the whole field of information retrieval is the research on how to actually, find the best metrics for matching the query and the documents, and what user information needs are, and whether you can personalize and things like that. So, as the most simple case, we just take the textual similarity between the query and the document. So if they talk about the same thing, they should have some relevant score. You want to rank them high. Common sense, okay? So there's two architectures to do so. And the more traditional is the so-called sparse retrieval. So we represent query and document as vectors of word counts. And it should resemble you something already. And we'll get to the details later. And then, like in the last couple of years, we have dense retrieval, so to say, where we actually use a language model to turn a query and a document into some embedding representation. And once we get it into embedding, we compute some similarities between the vector of the document and the query. So there's two approaches. One is based on just counting words, and the other is based on some latent representation in embeddings. So let's have a look in the traditional one, and why we are still talking about like tf-idf, and so we'll go to that, like the meaning of tf-idf. But you'd be surprised, these methods, although the dense retrieval methods are much better, the tf-idf methods, the sparse retrieval, are actually still very powerful. I mean, they actually run well on many tasks. They're super fast, very easy to implement, super efficient. So they still have place, among these whole deep learning approaches, dense retrieval and stuff like that. So that's why we're going to spend some time on explaining them. Because at the end of the day, it's very conceptually easy. You could implement it in an hour, maybe. So the vector model of information retrieval. Okay, here's the question. So what is vector of word counts? What is this? You have a document, let's say movie review, and you want to represent it as a vector of word counts. What is this? It has a name. We talked about this like so many times already. Yeah. It's back of words, exactly. Back of words. What is back of words? How do you do back of words? Yeah. You can take the average, you can just sum them up together, because then you get like the counts of the words. That's correct. Yeah. So you build a vocabulary and then represent each you throw everything in the back and represent it as a vector. The word which appears gets +1, the words they don't appear get like 0. Okay? Everybody's on that, like back of words. And here's an example with the actual back. So I'm taking these examples, by the way, from a chapter from the book by Dan Jarofsky and James Martin called, I forget the name of the book, by the way. speech and language processing, third edition, and it's online. And this lecture is heavily based on this chapter, and it's actually a very nice read. So you can get it for free. The PDF is on the internet. It's third edition, and Dangerous and James Martin are excellent researchers and teachers in the area. So just feel free to go there. The references in the slides. So they show this example, of a movie review. I love this movie. It's sweet, blah 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 blah. So something like from IMDb, I guess. Some movie review. Throw it in the back and get a vector representation, the length of the vocabulary. So it shouldn't be surprising. Any questions? No, good. And then, you want to basically represent all your documents as this so-called like term document matrix. So here you have all the terms which you just randomly picked words from the vocabulary. So this is just an example. So we have 4 words taken from the vocabulary, and here we have 4 documents which are Shakespeare plays. And this is just to represent that we have for each of the document, we have some representation. How many times the word occurs here in the document is just the raw counts. And I have to say, I don't know these. Do you know Shakespeare well somehow? You do? Okay, cool. So I know Henry V, but I don't know As You Like It, the 12th Night, and Julius Caesar. Okay, is it good? Shakespeare. It's complicated. I think you have to have some taste for literature maybe, or theater, or both. But anyways, maybe the authors of this book have this taste for literature and theater. I don't, so I don't know what these are about, but this is just an example of raw counts. So I think also having done, doing experiments on Shakespeare is kind of, it's for free, it's English, everybody knows it somehow, so it's easy to make references for some. Okay, so then we throw it. Oh, why do I have it twice? I don't know, it's a mistake. Okay, we throw it in the, this is the term document matrix, sorry, it's a mistake. So, and now we know also, like the another perspective on the documents in the collection is that, they are basically vectors, and we can represent them in this vector space. And here's just a visualization of if we focus ourselves on just 2 words in this, how many dimensions total we have? How many dimensions this vector space would have? The size of the vocabulary, exactly, which could be 100,000, 50,000, something like that. And here we just focus on 2 words, just to visualize that some documents are close to each other, and the idea is like, yeah, sure. I mean, this is why why back of words actually is a good representation of the overall kind of document in a way, because Henry and Julius Caesar, are they similar to each other? I have no idea. As You Like It and 12th Night, I have no idea either. I'm really sorry. But okay, let's say what they're saying. A specialization in blah, 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 blah. Corresponding to words battle and fool. Okay, so battle and fool. I think the fool should be something like a comedy, and battle should be something like drama, a serious thing. And maybe, these 2 might be some comedies, and these 2 might be some dramas. I mean, absolutely, I think like Julius Caesar is a drama. It's not a comedy. Yes, so Henry V should be also a drama, like it's about, like Game of Thrones style. Okay, and the others should be, I don't know, something else. Okay, so this is, how to think about the representation of words. Even if in a simple back of words, the vectors will put the documents in some collection, and then, based on some similarity of these vectors, we should find something similar, like to the query. The thing is that usually in the information retrieval area, we don't use these raw counts of words like 1, 140, and so on, but we compute something called term weight for each document word. So for each word, we compute term weight. So there's 2 variants of this weighting scheme. So we take this matrix and change these numbers somehow. We reweight them, so they kind of makes more sense for the information retrieval task. So this is good enough as starting point. If we take the average as you proposed, that would be also okay. Like normalizing basically by normalizing the vectors could be also okay. But for information retrieval, there are some more not advanced, but more like fitting the task weighting schemes. One is tf-idf, and there's one variant called tf-idf called BM25. We're not going to talk about BM25 in the detail today. There's just a simple formula how to compute this. But BM25 is still powerful in weighting scheme for information retrieval these days. So, and tf-idf is an abbreviation of something called term frequency and the inverse document frequency. So we're gonna introduce them right away. So the term frequency, frequency means just basically like counts. It's not about frequency, like how things oscillate. It's just a counts, like how many times, how frequent a word is, means like how many times it appears, just about a term. Because in physics, I guess it has a little bit different meaning. It's not just a count, it's the, how things oscillate. So frequency means how frequent the word is. And the idea is that, of course, words that occur, so we are in one document, and the words that occur more often in a document are likely to be information about the document's content. So if you have an article and it's like all the time about Julius Caesar, Julius Caesar, Julius Caesar, Julius Caesar, obviously the article is somehow more about Julius Caesar than it's about, I don't know, like Cleopatra, and vice versa. So it's very kind of very intuitive way of weighting the scheme, weighting the terms. And we usually take the word frequency and use a logarithm of 10. So basically dampening the scale of the influence of this particular word. And the intuition is that if the word is appearing 100 times in a document, it doesn't make the word like 100 times more likely to be relevant to the meaning of the document. So by taking a logarithm, basically if it appears 100 times, by taking a log 10, you get like the final weight will be 10. So it still has a high weight basically, the term, but it's not it's not an outlier. So you basically are smoothing down by this logarithm to take these extreme values basically down, while keeping the low occurrences sort of almost linear. So if we, let's define this term frequency as a count of term t in document D. Yeah. So if you take a log of the raw counts, like how about so what if there is no oh, that's actually interesting. I think the formula is wrong actually. So because the tf-idf score is if the word appears at least once in the document, you squeeze it through this log. But if the word doesn't appear at, yeah, I think this is correct. Yes. So there is some, of course, like logarithm of 1 is 0. So if the term would appear just once, it would end up 0 anyway. So that's why we add this 1, in front, just shifting basically by 1. And if the word doesn't appear in the document at all, of course, we keep it as 0. So this is like reweighting the non-zero weight, reweighting by the logarithm. Okay, that makes sense? Like we can make an example here. So for example, this one would be after TF would be 0 because this is 0. Logarithm of 80 is, I have no clue, like 7, 1.7, is it? Oh, right, yeah, sure. And this would be like 1.5 maybe, and this would be like 1.01. I don't know, I cannot do logarithms, just something like that. So we're basically dampening the high values down by the logarithm and keeping the small values. This would be, what is the logarithm of 7? I have no clue. I really have no clue. Anyways. Feel free to look up the book like there's actually like big example to compute the whole thing, but it's just an easy calculation. Okay, so this was the TF, term frequency. And then the second term, so the term this first one, the term frequency is telling you like for each term in a particular document, how much relevant is going to be. So how much are we changing the raw weights, like just the counts of the term, into something more helpful for the task, and we're dampening down by the logarithm. Then there is something else, which is the document frequency. And this tells you if a term t, how many, in how many documents the term actually occurs. So let's say you have a collection of 100 documents, and there's a word that appear in just one document, versus there's a word that appears in all the 100 documents. So which word is more relevant to represent the single document? Of course, the rare word is just more kind of significant for this. So what is an example of word, of a term, that most likely appears in every document? And, it, the, and so on. Particles, connectives. These are called stop words, by the way. Stop words, and they are just common. I mean, you cannot use just, if you like, searching for stop words is kind of tricky because they appear everywhere and they kind of discount it. By this document frequency, of course, the idea is that the term that is, occur only in few documents are useful for discriminating those documents from the rest of the collection. Yes. And vice versa, terms that are in the whole collection, like stop words, we just don't care. Okay? So this is the intuition. So what we're going to do is for each term, again, each term t, so term t is something like a word from the vocabulary. For each term t, we take, if we have the total number of documents, we basically divide it by the df index t is how many times the term, in how many documents the term appears, and the total documents over this will give you some sort of relevance. It's inverse. I mean, otherwise you could think like how many times it appears versus the overall number of documents would give you something between 0 and 1. You want to flip it over. That's why it's called inverse, which means the higher the number gets, the more rare the term is, right? If you have like 100 documents and it just appear in one document, you get a factor of 100. And again, we're dampening down by the logarithm of 10. So this is telling you like how rare the document is. The higher the number, the rarer the term, the term. And we are smoothing by the logarithm. Okay, makes sense? Cool. So, and yeah, this is it. Like the fewer documents in which the term occurs, the higher this weight. And the lowest weight of 0 is assigned to terms that occur in every document. Yeah, why is that so? If you have like 100 documents and the word appears in all 100 documents, you get 1, and log of 1 is 0. So it makes sense. So for documents for stop words, you will get 0 anyway, most likely, or something very close to 0. So the terms will be not relevant. So now we have two things, the term frequency and the inverse document frequency, and we need to combine them together in a very easy way. We just multiply them together. So we take the term frequency and multiply by inverse document frequency, and gives us the tf-idf of a term for a given document. Okay, so this is basically changing these raw associations first by taking the tf for each term. This would be like tf, and then to take the inverse document frequency for each term, multiply them together to get some scores. And we might end up in something very different from 1399, 4, and 3. For example, like the battle could be actually, I believe the battle will be more relevant just to a few documents. Like the word will appear only in fewer documents, while the words like good and fool might appear in or the word good might appear in every document. Something like that. Like you get the word, you get the terms related by their importance for the entire collection as well for the importance for the single collection. That's the whole idea, beyond tf-idf. Any questions? tf-idf, waiting. Very good. So now we know how to represent, like this is a different way of representing or reweighting the back of words to something which is much more useful for information retrieval. So now the question is like, if we have the document D and we have a query Q, we can represent them as vectors. How do we compute their similarity score? So we have tf-idf for, we know how to get a vector of terms in both in the document and both in the query. How do we get a similarity score of two vectors? You have two vectors. How do you find out they're kind of similar? What is a scalar product? Is it? Can you elaborate more? Can you elaborate more? Scalar product? Is it? Maybe it's a term for this. Yeah. Oh yeah, dot product. Okay, dot product. No, that's the German. How is it in German? How is it in German? Scalar product. Is dot product a scalar product? Oh really? Oh, that's confusing. Okay, dot product. It's okay. Okay, so you got a point for dot product. You get a point for dot product as well. In other words, what is dot product? What is dot product? Okay. Wow. Okay. I mean, it's mid-January, and we have the exam in 3 weeks. I'm pretty sure you should know what is dot product and how to do this, like what it really means, because we spend half the lecture on that and use it everywhere.
Yeah, the component wise multiplication.
It's component wise multiplication of the terms, yes, and we also take into account the different lengths of the vectors. So just a single dot product is not enough, because if you have vectors of differing lengths, they have different sort of, they would end up, they point the same direction, which means they could be similar, but they are dissimilar. So this is the cosine similarity is the thing. So you normalize the vectors both to one, and then you do the dot product. So, or if these are already normalized, you just take a dot product. Okay, cosine similarity is a thing. I mean, you should know the dot product. I mean, how to do this. And one way of using the dot product is to compute a cosine similarity. And if you wanna refresh yourself about the sort of like geometric meaning behind the dot product and behind the cosine similarity, just go back to lecture 3 or 4 where we just discussed this, like why this is kind of the relation to Euclidean distance and why is it kind of important. Okay, so cosine similarity is you can take a dot product of normalized vectors, and it will give you score of between what? It's interesting. 0 and 1 with the -1 and 1, right? And what is the meaning? When are two vectors similar to each other? If they are -1 or 1? Yeah, exactly. That's the geometric meaning of that, exactly. Okay, good. So this is how we do tf-idf for document. So just wrapping up now, we have a documents collection. We represent each document as a vector. We represent each query as a vector, and we do like cosine similarity to match, which document is closer, and we use this document score for ranking the document. So for our query, the higher the documents, I mean, the more similar documents are, the higher they should end up in the rank of documents which we are retrieving. Okay, and the particular way we're doing this is not just using the raw counts of one-hot encoding or just backup words, but we're weighting them by tf-idf because it's shown to be more useful for doing information retrieval. So this is the wrap up of this first part of the lecture, and we should be talking now about how do we know that our ranking actually produces something meaningful. So, or how do we evaluate our search algorithm basically. So let's say we do some ranking, maybe with tf-idf, maybe we have other methods. How do we know our ranking works well? So what are some standard evaluation metrics you know already very well? Like what do you use for some evaluation? Yeah. Accuracy, precision, recall, sounds good. I think this is a good start. So we're going to use the same precision and recall metrics we've been using. And what does it mean? I mean, imagine you have a query and you have a set of documents which are retrieved to you. So what is the main assumption for evaluating by using precision and recall? You have a query and you have a bunch of documents that your system retrieved. And you want to say something about precision and recall. So how do you know? Like, what do you have to decide on each of the documents? The rank is important, but how do you know that what you're getting is actually correct? You need to decide something. How do you know that if you have a query queue and a document D1, how do you measure precision, or what do you need to kind of assume? You need a knowledge of something. Let's call it like gold standard data. So what should be in gold standard data? You need to know, like, it's a binary label, so to say. You need to know that the document D1 is or is not relevant to your query. This is important. Otherwise, like, how would you know? How can you measure anything? So you make an assumption that each document returned by your system is either relevant to your query or not. And you can do this in different ways. You can either have a collection prepared. Basically, somebody annotates your query with all the relevant documents, which is, if you have like 1,000 documents in your collection and 100 queries, which means then you have like 100 times 1,000 pairs to be kind of considered relevant and non-relevant. So it's hard task to do. So what you can also do is you just retrieve the documents, rank them, and then look at, like, let's say top 10 documents or top 20 documents and then judge them post hoc. So let somebody decide, this is relevant, this is not relevant, this is relevant, this is not. Okay? But you have to know somehow like whether document is relevant to your query or not. Otherwise, you cannot say anything about precision and recall. Make sense? Yeah?
Why don't just assign score from 0 to 1 for the relevance and not a simple binary?
Absolutely, you can go more fine-grained, just beyond binary, yes or not, assigning a score. That's absolutely possible. It's actually harder. So how people are doing, how actual search engines, for example, are doing this is through some user feedback. Like what people click on seems to be relevant more than what it's not. So they use this and use it for, let's say, optimizing the ranker, preference learning, and all these things. But in the most simple setup, you just say it's relevant, it's not relevant. I'm pretty sure if you look at the example of the library search engine, it would be like the document number 1, not relevant, not relevant, not relevant, and maybe page 3 will like, oh, this is actually relevant. So this is the basic evaluation metric. Okay. Yeah, but for comparing two ranked retrieval systems, we need a metric that prefers the one that ranks the relevant documents higher. So if you just get a collection of documents and don't consider by the so precision basically is telling you like from the number of documents I'm getting, how many are correct. But it ignores the ranking. Like precision as a metric, as we know, it doesn't take the ranking into account. So we have to develop a technique that actually makes sense or utilize this rank, because what you want to have is relevant documents on the top, irrelevant on the bottom. This is what you really want. So there's a metric called mean average precision, but we'll get to that. So we'll start first with something for just for precision at rank. So here's an example. For some query, we are given like 10 documents back. And now we have this judgment like R for relevant and N for non-relevant, right? Somebody's annotating saying relevant, non-relevant. So we have this. And then for each rank position, we look at the precision here. So for position 1, we have just one document return and one of them is correct. It gives you precision of 1, like 100% precision, right? Okay, so from 2 documents retrieved, you get 1 relevant and 1 non-relevant, which means out of 2 documents, 1 is correct. It gives you precision of 50. Okay, so just to recall like how precision is computed. Any questions? Makes sense. Okay, so you continue basically for each rank and get out of the documents, you get the precision at each point, and obviously as you go down in the rank list, the precision typically goes down because you're starting to getting, like, depending on whether you're getting relevant or non-relevant documents. I mean, obviously what you're aiming for, what you want to really have is really high precision down the road. Like everything which is returned should be relevant as much as possible. You don't want non-relevant results on the top. We don't talk about recall because it's not really, I mean, if you have like, recall is actually hard to assess because you would have to know like how many relevant documents in total are in your collection. And if you have the entire internet, you have no chance to kind of judge this. So, but you can judge absolutely like, you know, the relevance of the first document, so like a precision-based metric. This is what matters if you have some ranking. Okay? Cool. So let's have some set of relevant documents at or above rank R. So then the precision of document D is precision measured at the rank at which document D was found. Okay, so what does it mean actually is I'm going through only those where a document has been found. So I'm ignoring now the ends. So I'm computing the precision here. I'm computing the precision after the next found document. I'm computing the precision for next found document, and I'm computing the precision for the next retrieved document, and so on. So just the R's. I don't compute the precision for the nonce. Okay, so this is what I'm doing, and I'm averaging these precisions for these documents. So I'm taking the set of relevance documents and basically normalizing. Basically, I'm taking the average of these precisions for the relevant documents now. This is for a single query, and if I have multiple queries in my document set, I'm just averaging over those. So this is like giving me like overall precision, like average precisions for each query, and for each query, I just care about at which rank I got a hit, basically, and how many, you know, what was the precision for this particular hit, and I'm averaging over those. And I take the rank somehow. What I care is mostly like 10 or 20 or 5, maybe, if I want to high precision. Okay? Yeah.
Why don't we take the rank into account? I mean, if we have a rank of, I don't know, position 20, and there's document that is relevant, this is less important than having a document on, I don't know, the top 10 ranks, and to find some non-relevant document in the top 10 ranks where you don't want to have those.
Yeah, so sure, that's a fair point. There's more metrics for doing evaluation. So the mean average precision is one of those. There is also one which is called NC non-cumulative gain or something, NDCG or something like that, which is basically iterating over the ranks, and it's like a slightly different metric, and it's also used. So the cumulative gain is different metric, MAP is different metric, and they have their pros and cons. I mean, the MAP is like the most simple one. But you are right. Maybe you want to go like through all the documents until like whatever is retrieved, and you wanna take this into account and weighting them by the rank, not just saying like what is relevant up till now, and then take the next one what's relevant up till now. Yeah, you're correct. So, but anyways, I mean, this will give you sort of some evaluation metric for if you have a set of queries, which is your test data set, gold standard data set, and you wanna compare your systems together. You wanna compare your systems among each other. These metrics are actually quite useful for this sort of retrieval, where you have a set of queries. Okay. So, any questions? Any other suggestions? Good, let's move on. So, where we are now. So we are talking about the sparse retrieval, so the tf-idf basically, and we are talking how to evaluate retrieval. And the whole idea is to have the retrieval useful for getting relevant documents for our answer generation. Okay, so just I'm trying to put things into the picture. So let's talk about dense information retrieval. And what does it mean? I mean, I do have, let's say we have a query, which is some bunch of tokens, lorem ipsum, and we have the document, which is also some bunch of tokens. So how do you turn them into vectors, not using backoff words? What could be a better representation of documents as vectors? After spending the whole semester with deep learning, we can do something like sentence BERT. Yes, sentence BERT. So what is sentence BERT doing? So it's basically taking single embedding for the entire sentence. How does it work? It's employing a BERT encoder, how it's trained on some contrastive learning and things like that. So basically you can do this. You can use, I believe you could use just like a GPT model, like decoder model. You throw in the text, and the last vector coming out of that could be your text representation as well. You can take an encoder and take, like in the BERT case, you can take the CLS token. This could be a representation. So there's pros and cons. There's different ways of representing text. I think these days, I'll get to that. These days, the decoder models are actually heavily used. But sentence BERT, yeah, that's good. I mean, sentence BERT is one way of representing. So basically, use a transformer model to convert a document into a vector representation. And the idea again is you're optimizing for similarity of these documents. So similar documents in terms of content, whatever it means, should have similar embeddings in the vector space, which is like dimensionality of the embeddings, 1,000, 2,000, whatever. And there's you mentioned sentence BERT. We also talked about sentence BERT in one of the lectures, but of course these days there's like gazillions of other models. And I just had a look yesterday on some of information retrieval benchmarks, because there are benchmarks. So if you go to Hugging Face, I hope it's readable to some extent. You can zoom in the slides if you will. But there's plenty of benchmarks comparing on different data sets. I think here is one example of multilingual benchmark on 22 languages, 29 tasks. So I don't actually know what these tasks are. I just look it up on the leaderboard. If you're building a system, you want to be number one, and then that's what makes you rich, and you can sell the product well. So the number one is something called Voyage Large. I don't know where it comes from, but the second one, which is Octane embedding 8B. So I had a look. It's text embedding. So I'm just quoting from the Hugging Face page. Octane embedding 8B is a text embedding model designed for semantic search and retrieval tasks. This model is fine-tuned. Okay, so this is a model which is fine-tuned from QN embedding 8 billion and supports multiple languages, providing high-quality embeddings for various applications. And the QN model is okay. So this is the latest proprietary model of the Qwen family, specifically designed for text embedding and ranking tasks. So you can fine-tune some decoder model. I mean, these are mostly decoder transformers. You can fine-tune the model for producing, ranking, and for producing good representation for ranking and search as well. So this is what we need to do these days for a state-of-the-art sort of representation and turning a document and a query into embedding. So one of those. And then you have to choose wisely, because some models are bigger, some models are smaller. So maximum number of tokens here of those is 32,000, and the embedding dimension is 4,000. Yeah, so basically turning every document into 4,000 vector. So the question is, how do you do the search now? You have a database of, I don't know how many documents can you have in the collection, like 500,000. You're a big company, you have 500,000 documents, you turn them into vectors of size 4,000 something, and you want to search in them. How do you do this efficiently? Any ideas? Like somebody who's, yes. That's an option. Like, I mean, my solution would be very technical. So there's things called vector databases. vector databases, which do support now like dense retrieval. So you put a vector into like this, like SQL database, but they have support for storing vectors, and they have fast algorithms for searching in these dense, like clustering or grouping. I think this is one of, and I think the algorithm is called FASS 2017 Facebook, something like that. So like for efficient and fast search in vector databases. And so I'm not using them in production, but I know like Postgres has a dense representation support. I don't know about MySQL if it's there. Is anybody using these things? No. Yeah. PG vector, exactly. Yes, PG vector is in Postgres. You're right. Yes. And maybe Mongo has some search support for that. So now we're entering the realm of actually building a product, and I have to say I have no clue because I'm not doing this like on a daily basis. But I'm just once in a while I get familiar with something. So this is more now. We're coming to like engineering solution, how to do this fast, efficiently, how to store the vectors, how to make it really accessible. And there's tons of out of box these vector databases for your RAG, for your retrieval augmented generation. And I hope we have something for the afternoon for the exercise, something in place. I don't know what Justin prepared. It might be a phase algorithm or something. There might be some vector database. Even like this, how's it called? So there's like very simple SQL database, like in memory, and it also has now support for vector search. But I forgot the name of the database. Oh. Do you know this database? Like it's very small SQL database in memory. Say again? SQLite, yes. So I think like even SQLite has now support for vector databases. So you can, if you have small collection, you can just put it into memory and it's very fast and efficient. Yeah, SQLite. Thank you. Okay, so how RAG actually works is in a way very simple. So then let's say we have another query, not asking about the museum, but where was the premiere of the Magic Flute? And if you're lazy enough to just go to Wikipedia to the Magic Flute and read, you can ask a very powerful LLM and burning GPUs all over the world, and the GPU will go to the retriever. I mean, turning this into embedding vector, doing the retrieval part, which we are just talking about, could be using BM25, tf-idf, or dense retrieval, depending on the size of the database. You get a corpus of documents, and you get the relevant documents typically. So what is limiting factor for the number of documents you want to retrieve? Sanity check. How many documents you want to retrieve? The size of the context of the LLM for answering. You have to fit it into the context, into the prompt. So you get, say, like, I don't know, 100 documents maybe maximum. If you have 1 million tokens, well, this should fit like 100 documents depending on the size. Yeah.
You don't want to blow up the context just for RAG. You want to preserve some space for.
For what?
For going on with the conversation.
Well, of course. I mean, if you're optimizing for the whole conversation, you want to blow up your context just for the RAG, but you can just search the document, get the answer, and call it a day, and then you're good. Yeah. So it depends. It depends on what the RAG is about, of course. And then you combine both in some prompt. So basically, you get the retrieve documents in plain text, put them into the prompt, and let the LLM to generate the answer, the premiere of the Magic Flute. 1791. Who wrote the Magic Flute? I guess it was Mozart. Yeah. So we should ask LLM right now. Can you ask LLM who wrote? No, don't do this, please. Just go to Wikipedia. Magic Flute. No. I mean, I think it was Mozart. We should know this. Anyways, and there's and like how you generate the answer. There's multiple ways to do this, but just the simple one is just you put it into prompt and generate it. So there's these two steps. Call the retriever, return a couple of documents, top K documents, create a prompt that includes these retrieved, and call LLM with the prompt. And the prompt can look like this. So you just basically copy paste the retrieve passage, the retrieve passages, By the way, whether this is a full document or this is just a part of the document, it also makes a difference. So most of the time, you don't want to put the full document, like the full Wikipedia page, the full, I don't know, CNN News page. You just want to maybe split it into some subparts, such as paragraphs or some other chunks. Because if the relevant information is just in one sentence, for the model, it's actually better to see this one sentence than searching this in the prompt for the full text. So that's why it's called passage here. So passage. Sounds French to me. Is it French word? I guess so. Passage. Okay. And we have k of them, and then you might say, based on these texts, answer. I would say, please answer. Please answer this question. What year was the premiere of the Magic Flute? And I would add some other crap like think step by step and be a nice guy, and all these kind of things that people are used for behaving nicely to LLMs, whatever. So this is it. This is the simple one. The extensions is you can extend it in many different ways. So for example, now thinking in a, let's say, production-based sort of LLM, I mean, you want to call direct just if you really need this, for example. So if there's, you want to do maybe some classification of the questions coming in and deciding ad hoc, like, oh, do I need to call some agent? So this is called agent-based rec, where the system decides when or whether at all to call some agent and for which collection and so on. So it's kind of like dynamically choosing like the context, not blowing up everything for like resources and not wasting resources for rec if you don't need this and things like that. So this is very clear. It's more like an engineering way of how to do like this kind of resource efficient way. The other is that the issue with I mean, we're talking about issues like asking question just LLM directly, and we talk about hallucination as a big issue, and that rec could be a way to remove hallucination, but not at all. And there's many reasons for that. So first, there might be noise in the retrieve passages. Some of them may be irrelevant or even wrong, and could be unhelpful order. So some RAG architectures use a re-ranker. So basically, you get your documents ranked, and then there could be another pass of these ranked documents just to re-rank them. So for example, if your ranker or your search is just BM25 or something very crude but very fast, and you get many documents, you want to do something which is much more fine-grained and re-rank these or extract some information from these documents with some, like, let's say, heavyweighter tools. So LLM, for example. So like 2pass will give you much more precise answer than just using the ranker as an LLM, for example, dense retrieval. So there's tricks to do so, and the best way is you need some good evaluation metrics to compare apples to apples, not apples to oranges. So a re-ranker could be very helpful. And also, like, what we really want for regs is some attribution of the answer. So you want to know where it comes from, or it's being known as knowledge citations or answer attribution. So for example, this is the one paper from NLP 2023. When did US break away from England? What? Okay, this is some 18th century. When did the US break away from England? And you want to answer the question. There are some retrieved documents, and what you want to do is to link the answer to the documents and also make sure you're citing the references. So it makes it somehow more trustworthy. I mean, if you can attribute your generated answers to some actual documents, it's helping you to, I mean, you as a reader kind of trusting more the documents. And I think like these days, ChatGPT has this, like, for if you ask for factual questions, it has like links to the URLs. I seen this. I asked for, what did I ask for? Something very stupid. Not where there's a Louvre Museum or something along these lines. And there was some references. Yeah, what is the best model to run on small GPUs these days? And it was very wrong answer. But there was a reference to some blog post, which I didn't read, of course. So anyway, I mean, in this case, it didn't work. But as you might see, it's I believe it's a way to progress, like being faithful and truthful for some facts in the database. It doesn't prevent hallucination. That's a point. Like the LLM basically decides on its own when it's pulling up information from the context, when it's pulling up the information from the feed-forward layers, from the parameters. It's hard to tell. Like it's a big monster. But answer attribution, and how to do answer attribution is very easy. Just prompting. Like write an answer for the given question using only the provided search results, some of which might be irrelevant, and cite them properly. Always cite for any factual claim, please. Okay, so this is how they constructed the prompt. It's really amusing how these things work. Like, just prompt it. This is very cool. But as I said, like answer attribution can be unfaithful, as one of these later papers, 2024, showed. These approaches do not account for attribution faithfulness. That means whether selected documents influence the LLM during the generation or not. The presence of some relation, entire relation, so whether the phrase is relevant or high semantic similarity, does not imply that the retrieved document had an influence on the answer generation process. So hallucination is really a big issue, and there's no easy way. I mean, as long as you just let the LLM generate something, it's hard to steer it like in a hard, let's say, hard constrained way. And it's an active area of research, I would say. And also very important for factuality and trustworthiness, so to say. And as I said in the beginning, I mean, we have beginning of 2026, so RAGs are here since just a few years now, and they seem very powerful. But one of the first papers I just want to mention is from the group of Sebastian Riedel, who was there, Tim Rock-Teschel, and others from, I believe, Facebook back then. 2020, how context affects language models' factual prediction. So even like in the early papers, they demonstrated a simple technique to greatly improve factual and unsupervised closed question answering by providing context documents as additional inputs. Okay, they used Oracle documents, blah blah blah, but found that using off-the-shelf information retrieval, so I guess back in the days they just used tf-idf, is sufficient to achieve performance on par with the supervised, and so on and so on. And they also already back then found that that the language models are brittle, so easy to break, so to say, and factual predictions, where if there is a noisy and irrelevant context, you can actually break the documents. And there's another research I just remember top of my head is from the group in Stanford and LawX project, where they use RAGs for legal questions. And even with RAGs, like the RAG is helping the model not to hallucinate in legal questions, but it's just disastrous. The performance for legal question answering is really, really bad, even with, it's hallucinating like as crazy as you might get. So there's a long way to go. And this concludes the lecture. I would suggest, have a look at this book from Dencherevsky and James Martin. And we'll have some fun doing RAGs today in the exercise in the afternoon. Okay. Any questions? No. Okay. Thank you. See you later.